Hello everybody, this is Dr. Yüksek, and in this chapter we will talk about magnetism, and we will learn how a magnetic field is created, how moving charges will create a magnetic field, or how a current carrying wire will create a magnetic field. And also we will discuss on right-hand rule to find the direction of the magnetic field. If you remember, we had talked about this right-hand rule before, and we will remember it here. And also we will talk about several laws about magnetic field in this chapter. And here you see the long-range forces that we have learned last semester. You know what does that mean? And here there are three examples. Oops, sorry. Let me change my pointer. And there are three examples here: gravity, electrostatic force, and magnetic force. For gravitational force, this is the equation as you can see here, and it depends on mass of two objects and the distance between them. So that's why we can say that force is created one of the mass, and also it affects the second mass. For electrostatic force, again, it depends on two charges, and it depends on the values of two charges and the distance between them, inversely related to the distance. This force is created by one of the charge, and also it affects another charge. For magnetic field or magnetic force, we are gonna learn what is the equation for this by the end of the class, by the end of this chapter. And we will see that, again, this magnetic force is created one of the moving charges, and also it will affect the other moving charge. And here we will talk about geomagnetism, which means that our planet Earth acts itself as a large magnet. Why? Because the interior of the Earth divided into layers by density, and in very inside of the Earth, there is a core, and this core has two parts. One is solid inner core, and the other one is molten outer core. This core is mainly made up of nickel and iron, so that's why we call it as metallic core. And in the molten outer core, or in the molten metallic core, the moving charges will create magnetic field. So that's why we can say that Earth's magnetic poles arise from the current in its molten iron core. When you look at here, you see the geographic poles of the Earth. This is geographic North Pole, and this is geographic South Pole. However, when you look at the poles of Earth, when you think about it as a magnet, we see that its magnetic pole are offset slightly from the geographic poles of the Earth rotation axis. So geographic North Pole is actually a south magnetic pole, as you can see here. This is the south magnetic pole, this is the north magnetic fold. So this south magnetic pole points towards the geographic North Pole. So that's why we can say that the North Pole of a compass needle is attracted toward the geographic North Pole of the Earth. And here there are some observation of magnetism, and which means that each magnet has two poles. One is north and the other one is south pole. And whenever two magnets are bring together, the same pole will repel and the opposite poles will attract each other. So that's why north or south will repel each other. However, the reverse opposite poles, north-south, of two magnets will attract each other. Another observation on magnet is when you cut a magnet in half, still it will be a magnet, but it will be weaker, which means that we will have two small magnets whenever you cut the big one. Still, both magnets will have north and south poles. So that's why from here we can say that there is no magnetic monopoles, which means that each magnet has definitely two poles. And none of the magnets has only north pole or only south pole. So all the magnets have both poles, north and south poles. This is very important. And magnets, when you bring the magnets close to some materials, it can pick up certain types of materials, not all of them, such as iron. If you bring a magnet towards an iron, you will see that either pole, doesn't matter north or south, both of them will attract the iron. And here you see a magnet and you see a charged rod. You can think about an electroscope. A magnet does not have, or an electric charge does not have any effect on a magnet. So magnet is, none of those will attract each other. And normally, if we were in the class, we would do this simple experiment, and you will do some observation. You were gonna use compass and iron fillings to map the strength and the direction of the magnetic field around a magnet. But here, I have included a video by Dr. Hassel that explains a magnetic field, and he also shows some example of iron filling and how this iron field when you put a magnet inside the there was a box over there, so you will see when you watch the video. And from this observation, you will easily answer those two questions. How does the strength of the field vary with distance from the magnet? And how does the field direction relate to the poles of the magnet? And you will see that the strength of the magnetic field will decrease when you increase the distance from the magnet. And then when you look at the field direction, you will see that the field starts from one of the pole and it will end up on the other pole of the magnet. And here you see a current carrying wire, and you will learn that a current carrying wire creates a magnetic field and it behaves just like a magnet. So on the left hand side, there is a rod, but there is no any current. So that's why when you put compass around the rod, there is no any change in the needle of the compass. Still, it shows the north pole of the Earth. This colored part of the needle shows north, and the white part shows the south. This is north, this is south. As you can see here, it doesn't change in any of the in and of the campus. However, on the right hand side, there is a current that goes through this road, and you see that when you put campus around the road, the direction of the needle changes. So as you can see here, each colored part shows the direction of the magnetic field. I'm sorry, magnetic field. So from here we see that it creates a magnetic field. A current carrying rod creates a magnetic field. This phenomenon is discovered in 1819 by scientist Oersted, and he implied that, or he concluded that there is a relation between electricity and the magnetism. And here we will learn how we will find the direction of the magnetic field by using right-hand rule. It's very easy if you follow these 3 steps. The first step here, first of all here, look at, this is the rod and it has a current, upward current. The first step is point your thumb, right thumb, in the direction of the current, as in here. This is right, oopsies, here. This is the right thumb in the direction of the current. Then the other 4 fingers, you will curl your fingers around the wire to indicate a circle. So you make a circle when you curl your finger around the rod or around the wire. And then at each point, the direction of your magnetic, at each point, your fingers, the direction of your fingers will show the direction of the magnetic field around the wire, which means that this is the circle that you create with your finger. So here it is the direction of your finger. 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 As you can see here, at each point, the direction of magnetic field changes. So you will determine this from the right-hand rule. So it is that much easy. And here you see the magnetic field lines around a current carrying wire. And right here, you see a notation for vectors and the currents. This is for vectors. This is for currents. If a current goes through into the page, this is the notation that we use. And if a current goes out of the page, this is the notation of this. In terms of the vectors, if a vector point into the page, we make a cross, as you can see here. If a vector points out of the page, we just put a dot. So those are just notation that we will use in this chapter. And here, there is a think pair question. First of all, read the question and try to answer it by yourself. And now let me try to explain how you will find out. In the question, it says that there is a long straight wire. This is the wire. Oopsies. This is the wire. And it extends into or out of the page. The current in the wire is the question that we will find out, whether is it into the page or out of the page. How we will understand this? By the direction of the campus needle. If you look at here, let's make a circle around this. Oops, my circle is so bad. Okay, So the colored one points to the north, right? So which means that points to the direction of the magnetic field. So magnetic field in this direction at this point. Here it is in this way, and here it is towards to the right, and here it is towards up. So to be able to have this direction, whether you should point your thumb into the page or out of the page. If you make into the page, then at this point, just do it when you are figuring out. Just put your direction of your thumb into the page, into the screen, and then curve your finger. And at this point, you will see that it will point downward. So that's why we understand that it is not into the page. Now let's change it. Let's make it out of the page. If you make the current out of the page, point your thumb, right thumb, in the direction of the current, which means that out of the page, and then curve your fingers around. And you will see that at this point, it is up, at this point, it is left, it is down, and here it is right. So that's why we can say that the current in the wire is out of the page, which is B. And here, indicate direction of magnetic field for the following wires. Arrow shows direction of current. For A, in part A, this arrow is to the right, which means it is the direction of the current. So put your thumb in the direction of your, let me change my thumb first. So this is the current, right? So put your thumb in the direction of this current, and then you will see that once you make a circle around this wire at each point, so here it will be into the page. And when you think about the circle right here, it will be out of the page. For part B, this time the current goes up. It is the direction of current. At the same time, it's the direction of your thumb, right thumb. So now make a circle around this. Once you put your thumb in the direction of the current and curl your fingers around the wire, you will see that here it is into the page, right? And here it is out of the page, and here it is to the left, and here it is to the right. For part C, this is the direction of the current, so which means the direction of your right thumb. So make a circle around it. Now, when you curve your finger around the wire, you will see that at this point it is into the page. And here it is out of the page. For part D, this is the direction of the current and the direction of your right thumb. So make a circle around it. But you will see at this point it will be into the page, to the right, out of the page, and to the left. Now, here there is a circle wire. It's a loop that we call it. The current flowing clockwise this way. This is the current. For example, if you put your thumb at this point in the direction of the current, and if you curve your finger around the wire at this point, you will see that the magnetic field lines into the page inside of the loop and out of the page outside. It's the same thing here. It doesn't matter where you choose, here, here, or here, or here. For example, oops. For example, here. We said that this is clockwise. Click pen. So this is current. We just did how we will find out the magnetic field line at this point. This is the current, this is the current, and this is the current. Doesn't matter which point you will choose to decide the direction of the magnetic field. Now let's assume here. If this is the direction of the current, put your thumb in the direction of the current and curve your finger around the wire. Make a circle. And you will see that still the magnetic field inside of the loop is into the page, outside is out of the page. So we can say that all the way inside into the page and outside is out of the page. Here, for the reverse, the current flowing is counterclockwise direction. Current, and current. Doesn't matter which point you will choose. Let's choose here. So if you put your thumb in the direction of the current, then you curve your finger around the wire, make a circle. You will see that this time in the outside it will be into the page, and inside it will be out of the page. So the same everywhere. So this is how we will find out direction of magnetic field for a current carrying wire. Those are some of the examples. And here in this slide, you see how you will calculate magnetic field along magnetic field created by a current carrying wire. So as you can see here, the equation is mu0 I over 2 pi r. Mu0 is permeability of free space. It's just a constant and it's given here. And I is the current. It depends on the current that goes through the wire. And 2 pi is again constant, and r, it depends on the distance. So as you can see here, magnetic field is directly proportional to the current. However, it is inversely proportional to the r. So that's why magnetic field line is decreasing. The strength of magnetic field lines decreases when you go away from the current carrying wire. This is the equation to find out the magnitude of the magnetic field. And for the direction of the magnetic field, as you can see here, you will use right-hand rule. And in this slide, And here you see a loop and a permanent magnet. And you see that a current carrying wire or current carrying loop, the current carrying loop produces a magnetic field identical to a permanent magnet. On the right hand side, this is the magnetic field. It has both sides, north and south, and the magnetic field lines emerges from the north pole of the magnet, and then they will end up at the south pole of the magnet. For a current loop, loop means a circle that we do in the previous slide as an exercise. And think about, you have a loop, you have a circle, and the circle is perpendicular, vertically perpendicular to the screen of your computer. So when you think this, which means that it is a kind of circle, right? So the current at this point is out of the page, which means that here, and the current right here, it is into the page, right? So when you put your finger in the direction of the current right here, and then your thumb in the direction of the current right here, and then if you curl your fingers around the wire, you will see that this is the direction of the magnetic field, this point. So do the same thing at the bottom. This time it is into the page, the current is into the page for this circle. And when you put your thumb in the direction of the current, and if you curl your finger around the circle, you will get this circle to create the magnetic field. So that's why we see that magnetic field lines emerge from this side, and then they enter on the left hand side. So that's why we can assign the pole of the loop as north on the right hand side for this loop, for this specific loop, and on the left hand side we can assign as the south pole. So that's why we say that both of them are magnets. And here, maybe in this slide, it's much easier to see. This is the loop and this is the current. At this point, it is out of the page, and here it is into the page, the direction of the current. So that's why you can easily find out the magnetic field lines at each point. So our right-hand side is the North Pole, left-hand side is the South Pole. And on the right-hand side, you see the units of magnetic field. Generally, we use Tesla in SI unit system. 1 Tesla is equal to 1 Newton per ampere meter. And gas is in the CGS unit system. And here in both system, you see the Earth's magnetic field. Earth's magnetic field is 0.5 G, gas means, and it is 0.5 times 10 to the minus 4 Tesla. But as I said, we generally use Tesla as a unit of magnetic field. And here you see that magnetic field of the loop is proportional to its magnetic dipole moment. If you remember, in electricity, we had learned electric dipole moment, which is P, right? And we were calculating it by charge and the distance between two charges was a dipole, right? With same amount of charge but different sign, plus Q and negative Q, makes a dipole. And then, so the electric dipole moment was equal to Q times the distance between them. In a similar way, we define mu, which is magnetic dipole moment for this chapter, and we see that it is perpendicular to the loop, and still we determine the direction of the magnetic dipole moment by right-hand rule, which means that we will curl our fingers in the direction of the current, and our thumb this time shows the direction of the magnetic dipole moment. Its magnitude is equal to current times the area of the loop. I is the current, A is the area of the loop, and it points from south pole to the north pole of the loop. And here you see the torque, and once you know magnetic dipole moment, when you find out cross multiplication of magnetic dipole moment with magnetic field, you will calculate the torque. By the way, the magnetic dipole moment is a vector, it is not a scalar. And in this question, where is the north magnetic pole of this current loop? So think about, this is a ring, it's a loop, which means that we can make a circle horizontally. Okay. So at this point, the current is out of the page. At this point, the current is into the page. So if you put your finger in the direction of the current right here out of the page, you will see that at this point, this is the direction of the magnetic field. So right here, it is into the page. Make a circle around it. And it is the direction of the magnetic field. So that's why we see that from upper side of the loop, the magnetic field lines enter, and from the lower side of the loop, the magnetic field lines leave. So we have learned that for a permanent magnet, magnetic field lines emerge from the north pole and enters from the south pole. So that's why this is south, this is north pole for this loop. So the question was north pole of this loop. So it is the bottom side. Yes. And you can nicely see here the magnetic field lines at each point. And another question, what is the direction of the current in the loop? So this is permanent magnet, this is the loop. Loop is vertically aligned. So north, south, from those arrows we understand that they repel each other. If they repel each other, the right side of the loop should be south. Oopsies. I forget all the time to change the pen. So the right hand side should be south and the left hand side should be north. So at this point, if you make a circle and just try into the page and out of the page for the direction of the current, because the direction of the current will determine the direction of your right thumb. If you think about the direction of the current at this point is out of the page, Then when you curve your fingers around this point, you will see that it is the direction of the magnetic field. So from right hand side, according to this, from right hand side, the magnetic field lines emerges. So if it emerges, then this should be the north side. So that's why it cannot be the out of the page. Let's make it into the page at this point. So for into the page, the direction of magnetic field will be, curve your finger around this circle, right, in this way. So as you can see here, at this point, the magnetic field lines enter, and on the left hand side, it leaves. So that's why it matches with south and north pole of our loop. So that's why the upper part should be into the page. If this is into the page, the other part should be out of the page. But let's again check it. If this is out of the page, let's make a circle around it. Put your thumb, right thumb in the direction of the current, which is out of the page. So curve your finger around this circle, you will see that this is the direction of magnetic field. So that's why here it enters from right hand side, from left hand side it leaves. So that's why we can say that it is into the page at the top, out of the page at the bottom, which is B. Yes. And here we see that there are two loops, and those two loops can feel attractive or repulsive force on each other, like permanent magnets. So it depends on the direction of the current. If the direction of the current are parallel, then they attract each other. This is out of the page at the top, and at the bottom it is into the page. If this is out of the page, at the top, the right hand side is north and the left hand side is south. For the other loop, left hand side is south and right hand side is north. So that's why north-south will attract each other, as you can see here. However, for opposite currents, at the top, one is out of the page, one is into the page, and at the bottom, one, the reverse of it. Here, for the top, which is out of the page, right hand side is north, left hand side is south. For the one which is into the page at the top, left hand side is north, right hand side is south. So as you can see here, north-north will repel each other.